Hi, the topic of this video is a new MCMC algorithm with fast mixing properties for heavy-tail target distributions. Okay, this is joint work with Miha Bresar. So the setting is I take pi, which is proportional to a density on RD, that has polynomial tails. So in other words, the tail of pi is sort of sandwiched between two polynomials with different constants of this order. And here the power is minus v minus d. D is the dimension, and v is a positive parameter that essentially tells me how many moments pi has. You see, the tail of pi then decays as r to the minus v. Okay, so the objective is to find a fast algorithm, i.e. a Markov chain that has pi as a stationary measure such that I can sample its increments for the sampling from pi, from computing ergodic averages under pi. So applications abound, right? So in Bayesian inference, heavy-tailed priors would lead to situations where exactly this kind of thing is needed. Cauchy priors, student priors are common. Gelman and others have been documenting this for a while. Okay. The problem is that a standard MCMC algorithm such as random walk metropolis, Mala, or Hamiltonian Monte Carlo have very slow convergence rates. You see, after n steps, the distance between the marginal law of the algorithm and the measure I'm trying to hit is polynomial, right? It's n to the minus v over 2, and you see this v is this v here, right? So the rate is not good. Now, no U-turn sampler that people would use in such situations. There are no theoretical results of this type, but slowdown happens in practice, right? Now, really, one can also in practice see that the CLT fails, right? So what we're trying to do is we're trying to sort of understand what pi of g is, so the integral of some L1 function of pi. And what we do is we run a sampling algorithm for capital N steps, and then look at an ergodic average, which will converge almost surely to the quantity of interest. Now the question is, what is the error, right? So you see, I've got this Sn of g minus pi, I blow up the error, this should converge to a normal distribution, right? So when I run these chains, independent chains, a number of them, and I look at the empirical distribution, and I compare the CDF of the empirical CDF with respect to Gaussian CDF, I should see these dots lying on a line. Clearly, even for algorithms like ULA, like Euler scheme for Langevin diffusion, or Mala, they don't lie on a line, so really the CLT fails. So the problem is really there. So people have noticed this, of course, and what have they done about it, right? So in the literature, there's been several approaches. The first one was to simply sort of modify random walk metropolis with finite variance proposal, like Gaussian proposal, for example, to take infinite variance proposal. So do a proposal with alpha stable distribution, right? And then you can prove that the rate increases from n to the minus v over 2 to n to the minus v over alpha. You see, if I take alpha smaller and smaller, I get a better and better rate. But nevertheless, no matter how small alpha I take, I always get a polynomial rate. So this is still not a satisfactory thing. Now, this paper by Johnson and Gare from 2012 suggests to take an automorphism of the whole RD to sort of suppress the tails of pi and make them super exponential. Now, this, if you can do that, you will get a geometrically ergodic chain. It will not be uniformly ergodic, okay? And this method is really only applicable to random walk metropolis, because if you have if you have the gradient methods and you sort of dampen the tails too much, you get too much of super exponential tails, then geometric ergodicity goes out the window. This is a well-known fact. ULA even becomes divergent, right? It's not even an algorithm, but Mala is certainly not geometrically ergodic, right? So it's a delicate method in that sense. Recently, stereographic projection samplers suggest to take RD and map it onto a d-dimensional sphere via a stereographic projection in RD plus 1, okay? And the SPS, the resulting algorithm, is indeed uniformly ergodic, but really when I do the entire mapping onto the entire sphere minus the North Pole, pi needs to have d finite moments for this uniform ergodicity to hold, otherwise it becomes polynomially ergodic, okay? Now, A version of this algorithm is this CUHK-Sz sampler, which is even more recent, okay, which says that you should look not on the entire sphere, but you should look at a cap on a sphere, okay. But of course, that will sort of require the requirement on the tail of pi will be lessened because it requires only one moment. However, you have to deal with the fact that you are on a curved manifold with a boundary when you're sampling, and this has numerical cost, which we will see in numerical examples below. Okay, so what's our idea in this context, right? We are still going to combine these previous approaches, right? So the main idea is to take RD and shrink it onto a ball of some radius in RD. So we don't change dimension, of course, we just shrink it to a ball, and this shrinking will sort of put the tails on a compact set, and we'll sample on a ball. Okay, so we'll do that in two stages. The first stage, of course, this RC total is the composition of the two stages, but the first stage is the radial contraction, okay, the radial contraction, which will compress the heavy tails onto the unit ball. And then we're going to use an automorphism of the ball to correct the landscape that we obtain, okay, to maybe flatten it out. That's the idea that what you should be thinking about. And then RC total then has also some centering. This R is a parameter, how big the ball you can take, and it's just this has this decomposition, okay? Now, why ball, right? So ball is not arbitrary in this case. And the reason why it's not arbitrary is because we know from the literature on sampling of convex bodies, so this is a famous paper by Lovash and Vempala, that says that you want your convex set to have as few corners as possible. And a convex set that has sort of constant curvature boundary has, of course, no corners and will provide the best setting for the best non-asymptotic results. Okay, now to be more specific, okay, so how are we going to do this contraction, right? How are we going to do this contraction? And okay, so here is an explicit formula of this contraction that depends on this parameter beta, okay? But really the formula is not so important. What is important is that this contraction is going to be a radial contraction. You see every y is just going to be the length of y is going to be changed, and as the norm goes to 1, the length will go to infinity. Of course, it needs to cover all of RD, but the key thing is that the Jacobian of this transformation as the norm of y approaches the boundary is really of the same order as the norm of the map to the power d plus beta for this arbitrary parameter beta. Okay, so that's the key property that it needs to have. And this is just one very simple example of the map that has this property. Okay, and this one is not important. Any positive constant here will do, of course. Okay, this will guarantee uniform ergodicity of our algorithm, right? So you see, why? The reason is that if I pick beta smaller than the tail decay of my pi, then the pullback density, okay, on the ball via this map is going to be just pi of the sort of transformation times the Jacobian. Because of this requirement, this pullback density, it's clearly bounded. And then when you have a bounded density on a convex body and you run an algorithm on that, you're going to get something that's uniformly ergodic. And this will be uniformly ergodic for arbitrarily heavy-tailed distributions. Okay? Now, we need to sort of improve the landscape maybe. Okay, so when we do this contraction, the contraction will deal with the problem in the tails, so the problem in the tails, okay? But, okay, maybe there are still many modes or something like that, and in order to sort of deal with these modes, we have these parameters, the scaling parameter, the centering parameter, mu, but most importantly, we also have this additional automorphism of the ball itself, okay? And in order to look for this automorphism, okay, one can do that in a sort of systematic way using variational inference preconditioning, right? And it's clear what the target should be, you see, because you'll be running an algorithm on a convex set, and then these algorithms, of course, converge best if the target density is constant, okay? So you will you have a clear criterion on how you should be looking for this automorphism of the ball using the KL divergence from pi b, which is the sort of the pullback measure, and the uniform distribution on the ball, right? So this aims to flatten the mass. Okay, so that's the basic idea behind the algorithm. The algorithm is very simple now, right? So I want to describe how I go from xn to xn plus 1. So I first go back with my total diffeomorphism onto the ball. And on the ball, I choose my favorite Markov kernel on this convex set. I make one step, and I move back. Okay? So now the question is, what kernels Q can one choose? And this question has been answered already for us, right? Because this is a nice convex body in RD, right? So you can take ball walk, for example, which is just sampling, sampling on some ball of a small radius around it, and then if I just jump out of B of R, I reject immediately. And this is cheap, ignores gradients, but will have good convergence properties. I can do also hit and run in this situation, right? So this means that I choose a direction, and then I do a slice sampling in that direction on the over the line segment that is in my ball. Okay. Other possibilities are there. Also, I can use Deakin walk. I can use random walk metropolis with Gaussian proposals. I can use Langevin Monte Carlo. They all have good mixing properties, as you will see. Okay, so now there are two types of results that we prove. One type is this uniform ergodicity, and this is quite a universal result for this algorithm DCS. You see, as long as I take my pi, I choose the parameter beta so that pi satisfies this requirement, right? So essentially beta is smaller than the tail decay parameter of pi. Then for any of these algorithms that I mentioned earlier, also any of the values of parameters r, mu, and the automorphism tau, I always get a uniformly ergodic algorithm. So what does that mean? It means that there exist universal constants c and rho, such that universal, they don't depend on the starting point, such that the total variation distance converges geometrically. Okay. Now, this means that this algorithm really gives me uniform ergodicity for arbitrarily heavy tail polynomial targets. Okay, because I just, as I said, I have big beta in here. Okay. Now, for the non-asymptotic bounds, what I'm interested in is, given a fixed epsilon, okay, I want to know how big n is, so that when I start my chain with a law var sigma, how far am I from the target distribution nu, okay? So I want to be, so this total variation, of course, is not decreasing, so at some point it will become smaller than epsilon, right? So how big then n is in terms of the parameters of the model, including the dimension, which is the most important parameter, right? So in order to get non-asymptotic bounds for my algorithm, I need more assumptions, okay? Because you saw uniform ergodicity is sort of very generic, right? Any of the algorithms, Q I choose on the ball, or any of the values of the automorphism of R or the centering mu, it didn't really matter. I always got uniformly ergodic things. Here, I have to make assumptions on the pullback density pi b, okay? So the most important assumptions are the convexity and this isotropy, right? Which are, so you see, the convexity of this pi b will be guaranteed, at least asymptotically close to the boundary. The convexity is guaranteed by choosing beta so that my algorithm is uniformly ergodic, okay? This turns out to be the case. It's an easy calculation to do, okay? And then variational inference in practice, choosing this automorphism of the ball, really tries to enforce global convexity, okay? And this can be done, for example, explicitly for student T distributions. But in practice, it also works very well, as you will see from the numerical examples. Okay, now, but before we go to numerical examples, okay, so we have this theoretical result. This is a rigorous theoretical result that sort of guarantees that if I take a heavy tail target, my algorithm, this diffeomorphic contraction sampler, will have mixing time bounds of order d to the alpha, okay, where alpha is some integer, so it'll be polynomial integer, and here they're stated, okay, and they're essentially inherited from these various algorithms, ball walk, hit and run, Langevin Monte Carlo, and Deakin walk on the ball, that have been done in this sort of long-standing literature, on non-asymptotic bounds for sampling on convex bodies, okay? Of course, the assumptions are sort of various. The assumptions are on the previous slide, and perhaps the most interesting here situation is that we have hit and run here from a cold start, okay? it will be polynomial to be d cubed. Okay, so you see, I mean, this is how big n should be in terms of d. There's going to be some other constants that appear in the assumptions, right? And it says here that if I have hit and run, start from cold start, meaning that, you know, I start from an arbitrary point in my state space in RD, I will converge. I will have a mixing time that will be awarded d cubed. Okay. So now, mixing times for heavy tail target distributions for other MCMC algorithms are not many in the literature. For example, it is known that for the random walk metropolis, recently it was proved, for classical random walk metropolis with Gaussian proposals, the mixing time is exponential in the dimension, okay? Exponential in the dimension. DCS with the hit and run kernel on the ball sort of reduces that to DQ. But really any of these guys, you see, are any of these guys are polynomial. Okay, now this is sort of the theory. Now in terms of sampling, we're going to look at some examples how DCS performs against state of the art. Okay, we'll compare it to no U-turn sampler, to some real world benchmarks in posterior database, and to the stereographic projection samplers, which are these recent samplers for heavy tailed sampler. Okay. So here is a first example. So we simply take a skewed student T target distribution, okay, with 3 degrees of freedom. So the V is 3 in that case, okay. And so this is a heavy-tailed skewed distribution, and we run nuts on it, and we run DCS on it. And how do we run it? We take 50 independent chains, 20-second CPU budget on both, okay. Now, we know the ground truth, okay? So when we're estimating this probability, the ground truth is 0.03 roughly, okay? And so this is the DCS algorithm with ball walk on the sphere, okay? And the parameter, contraction parameter beta equal to 2, which is, of course, beta needs to be smaller than this 3, okay? So you see, it hits it pretty well. And here, of course, we compare to the situation from the JAX accelerating no U-turn. You see, no U-turn sampler has a professional implementation in STAN, this JAX accelerating implementation, and you see that this amateur implementation of DCS with a underlying ball walk dramatically outperforms this guy, and the difference is maybe even starker when we look at the first moment. Okay, this is a relatively small dimension, 200-dimensional example. Okay, so now. You see, if you really put the sort of random walk metropolis into the mix to see that this nuts is still really state-of-the-art in this context, right? You see, so here we've got random walk metropolis with Gaussian proposals, okay? So here we're looking at the mean squared error, okay? Mean squared error. And here random walk metropolis with heavy tail proposals would have half a moment, okay? So this guy performs better, as I was saying in the beginning, you know, the tails are thinner, the rate of convergence is faster, but this professional implementation of no U-turn sampler, of course, outperforms everything. But of course, if you look at here, DCS ball walk with beta equal to 2, you see the error here is 10 to the minus 7, while here the error is 10 to the minus 4, roughly, right? And here for the first moment, also our algorithm sort of outperforms the professional implementation of JAX nuts. Okay, right. This is the same distribution as before, right? It's this skewed 200-dimensional student T. Okay, right. Now, of course, in terms of the real-world tests, there is a posterior database now that contains sort of difficult real-world data sets with priors that have both heavy tails and have funnel geometry. So funnel geometry means this is a 3-dimensional prior or something like that, or higher dimensional prior, and then the mass is somehow very sort of in a very small proportion of the space. Okay, it's concentrated in some specific directions. Okay, and this GARCH11 data set is a time-varying volatility with a strict hard constraint boundary and a heavy-tailed ridge, okay, at this boundary. So both of these examples are actually outside of our theory, but nevertheless they show that our algorithm sort of performs well, is robust in this sort of context. Okay, so we ran that, and we ran the JAX nuts implementation, right? So for the this centered 8 schools example, okay, with heavy tails and funnel geometry, okay, so we get you see roughly 3 times improvement in the mean squared error for the first moment, and for the second moment sort of likewise or even more. And in the other example, sort of the situation is also so our own implementation sort of outperforms the stuff that you get out of STEM. Okay, so now a final example we need to compare with this very recent CUHK-Sz sampler, right, which is sort of designed to deal with heavy tail targets. Okay, heavy tail targets. So here D is 100 dimension. It's a skewed student T. This is an example from the paper. Okay, and so here we don't give a budget. We run 20 chains with 500,000 iterations. Okay, so that's the length of the chain. And then we look at what we get. Okay, so what algorithms have we used here? You see here, for example, we use, okay, so this is, you look at the mean, okay, you're estimating the mean of this distribution, and this is the mean squared error under the CUHK-Sz sampler, okay, so because this is, as I was saying at the beginning, right, CUHK-Sz sampler is on a cap in a sphere, and sort of computationally it is more expensive than just sampling on a ball, but in terms of the mean squared error, of course, the mean squared error is sort of reduced by the ball walk, DCS with the ball walk on RT. Okay. Right. Okay. So to conclude, this diffeomorphic contraction sampler is a new sampler that is uniformly ergodic for arbitrarily high heavy polynomial tails. It's got non-asymptotic mixing time guarantees, which awarded D cubed from a cold start in the case of hit and run. It has low computational cost because the parametrization on the ball is efficient, and it sort of outperforms the state-of-the-art JAX nuts implementation, as well as the stereographic projection samplers in these specific numerical examples we looked at. Okay, thank you very much for your attention. Here are the references.